let's get started with reinforcement learning. So far, what we have been doing was a data-driven approach. So our data was either in the form of images, or it was in the form of text, or it was in the form of speech, or even tabular type of data. But can we design a machine that is actually intelligent, that can collect its own data whenever it needs to? And that's the topic of reinforcement learning. You're going to have an agent that is going to interact with the environment, collect its own data on the fly, and then keep learning on its own without any supervision. And let's start with playing Atari. And what do I mean by environment? So far, I was asking you to do data exploration. Now your exploration is going to be a little bit different. So you need to explore the environment. For instance, arcade learning environment is a learning environment that is going to give you the simulations that you need. For instance, for this ping pong game or the other Atari game or many other Atari games. So now you have an environment that your agent is going to interact with. You can think of it as your data or the place that you're going to go into to collect data. Okay, you have an environment. Let's go into the math and try to formalize the problem. So we have an environment that we're going to interact with and then collect data from it on the fly. And the data that we're going to see is going to depend on the type of actions that we are going to take in that environment. So they are not going to be IID data anymore. And the way that the agent is going to see the environment is going to see it through the observation. So it's not going to see all of the details of the environment. It's going to collect some observations. And then because you want to write down an objective function, you need to tell your agent how good it is doing. So you need to give it some rewards or punish it sometimes. So you need to either define a cost or a reward. The agent is going to take actions in the environment, like in this figure here. It could decide to go left or to go right. That's an action. And the action is being chosen from a set of legal actions, going left, right, up, down, etc. And you can have a discrete set of actions. And we're going to generalize this later on to more complex actions where this could be a continuous set of actions that you can choose. But for now, let's assume it's discrete because we are doing Atari. What observations do we make? Our observations are in the form of images. So exactly as a human would see this environment, if they were playing it, we are going to simulate the same behavior. So our agent is going to see this image. And you can flatten it or not flatten it. Whatever that you do, it's going to be an image at time t. And then at time t, it made a decision, and then it's going to collect some rewards. This is a partially observed task. What do I mean? What is the definition for it? It's not enough for your agent to know only what image it is currently at, what state it is currently at. So it's not enough information because it's not going to know, is this ball going up? Is this ball going down? Is this ball coming from right of the screen, or is this ball coming from the left of the screen? So if the only thing that your agent is seeing is an image, there is no way for it to know where this ball is coming from. And that's important information. And because it's partially observed, the state of the system, we are going to define it this way. We are going to keep the entire history of the images that it saw and the actions that it took, or at least a portion of those, maybe the last few histories or the last few snapshots. So that's going to be your state. And this is going to give the agent more information, perhaps enough to operate in this environment. This is going to be a Markov decision process. I'm going to give you more detailed definition later on. But for now, these types of problems are Markov decision process, MDP. How are we going to work with this environment? If you're at time t, you're going to have a future discounted return. So you're going to collect your return today. You're going to follow some strategy, collect some return tomorrow from the environment, the day after tomorrow up until the end of the game, until you see the game over or you win or something happens. But then a reward today is more valuable to a reward tomorrow or 10 days from tomorrow. That's why you're discounting the return from future. So that's future discounted return at time t. We are going to define an action value function, which basically says, and this is optimal action value. So you have a policy that is mapping these sequences to actions. So as soon as you see your state, you should be able to decide and perform an action. And this is usually in the form of distributions. So we need a policy. We defined, and we are going to define our optimal action value function. But what is that? You're currently at time t sitting in state S, and you just took action A, assuming that you're gonna follow a policy, because you need to know your policy because you're interacting with your environment. What actions are you taking? Because those actions are gonna define your return, your future discounted return. And then you're gonna take an expected value, and this expectation is being taken with respect to the data that your agent is observing from the environment. So it sees an image, it decides to go right. It sees another image, it goes to the next state, it collects some rewards, goes to the left, right, according to the policy, and then it's collecting the rewards. But then I said this is optimal action value because you're optimizing, you're finding the maximum return with respect to the policies. So basically find the best policy that's going to give you the best return. And then if we remember, we were doing dynamic programming a lot of the times. When we have a complex problem, we usually define two parameters or one parameter. In this case, S and A are our parameters. And then we just take into account two time steps rather than the entire time steps into the future. If you do that for this problem, that's going to give you Bellman equation, and that's your equation. And this is a classical equation. So there is no need for us to go into details of how you drive it. We can just take it for its face value. There is Q star, there is Q star here. And then this is going to be a function of S and A. So you're currently in state S and you just took action A. And then you're going to look one step into the future. So you collect your reward today, and then you're going to estimate the rest of it by your optimal action value. So you're going to say from that point on, let's assume that we are going to take the optimal strategy, and that's going to give you Q star again. But then this equation here, the term on the left is a function of S and A. This term here has S, A prime, and S prime in it. We need to get rid of them. To get rid of S prime, you're going to take into account all of the possibilities that could happen in your environment. So you're doing an expectation with respect to that. So you're getting rid of S prime, and then you're getting rid of A prime by choosing the best action. So you choose the best action. So you do a maximization here and an expectation here with respect to S prime. And that way you're getting rid of A prime and S prime. So that's your Bellman equation in terms of the optimal action value function. And the action value is related to the future discounted return, given that you took action A in a state S, and you're following the optimal policy. This is classical value iteration algorithm, and it's usually useful when your action space is finite dimensional and K shouldn't be too big. And the other requirement is your state to be discrete. And if it is like that, it's going to give you some tabular function, because now this function, you can explain it in an Excel spreadsheet. For this state, for this row, this column, what is Q? And then you do value iteration. It turns out that the fixed point of the Bellman equation, it actually exists. And if you do value iteration, it's gonna, that function that you see up there is gonna end up being contractive. So it means that the fixed point is gonna exist. And then you're gonna do some iterations, some value function iteration. You start with QI, you start with one Excel spreadsheet, and then you do these operations, some additions and some maximization. And then that's going to give you another spreadsheet. And then you take that spreadsheet, you go to the next iteration, and then you keep repeating that. In the end, you're converging to the optimal action value. And as soon as you know your optimal action value, your policy is just this. The action that is going to maximize the action value is your policy. So at each iteration, you're going to look at your optimal action value. You maximize with respect to A, and you take that action. That's your optimal policy. But then we are living in the neural network era. We don't want the assumption, you don't want to make the assumption that K is small, and you don't want to make the assumption that S is discrete. We want to make the assumption that it's actually images and continuous. So one idea is to approximate Q star, what you have here, with a neural network. And that's going to be called Q network because you are putting a network on your Q. So that's the easy part. As soon as you see a function, you're going to approximate it with a neural network. Perfect. So many of the trouble in reinforcement learning comes from writing a good loss function. So you want to optimize the parameters of this Q. But what is the loss function? The loss function is going to come from the Bellman equation. So that's why we had to go through a lot of trouble to write down our Bellman equation. As soon as you write down your Bellman equation, your reinforcement learning algorithm is going to turn out to be a simple supervised learning algorithm. How? You want this term to be 0, okay? Let's call the right-hand side y. This is the output data. S and A are going to give you your input data. So you have S, A, and Y. And then you want these two terms to be very close to each other. So you square them, and then you compute the mean squared error on your state and actions. And rho is some abstract probability distribution. Rho, you don't know its functional form. You just know it based on sampling, based on interacting with your environment, based on going left and right. So that one is going to become more clear as we write down the algorithm. But in the end, this is your loss function with respect to the parameters. And it's a simple regression if you think about it. But what is yi? Yi is exactly this term on the right of your Bellman equation. So it's the expected value S prime sampled from your environment, your return plus gamma, your discount rate. You choose the optimal action at that point in time based on some parameters. And these parameters are the parameters of your neural network from the previous step. Because this guy here needs to be deterministic. So you need to know what is the value at the end. So if you put theta I here, the same thing that you have up there, your algorithm is going to collapse. Because for supervised learning, you need to know what is S, what is A, what is your input, and what is your output. So the output needs to be fixed, not trainable. And this is one way of doing it. And this is not the best way of doing it. We're going to see later on improvements upon that. So your loss function, the moral of the story is that it's coming from your Bellman equation. That's why you wrote down your Bellman equation. That's going to give you a loss function. And as I mentioned, this rho here is just a probability distribution. It's an abstract notation. You're never going to see it when you implement your algorithms on your computer, but you can sample from it, from your environment. That's why you need to know what is your environment. So you need to know your environment. So what are the properties of this framework? It is model-free. By model-free, we mean that you are not modeling your environment. So you are not modeling the archived learning environment at all. So you're not learning your environment. You're not learning your dynamical system. The only thing that you're learning is this optimal action value function. And it's off policy. You are not putting a neural network on your policy function. You are putting a neural network on your action value function. But then the policy is going to be a greedy strategy policy. If I know my Q, I can take actions based on Q. How? You just maximize Q with respect to action at this current state. So given the state, if you maximize this, you're going to know the action. And that's going to be your policy. There is a problem with supervised learning. For it to work, yi's need to be sampled identically and independently from your distribution. So they need to be IID. In reinforcement learning, these samples are not going to be IID because they depend on the parameters of your neural network from the previous stage. And they depend on the actions that you took yesterday or 2 days from today, etc. So they are not going to be IID. They're going to be highly correlated. They're going to depend on whatever actions that you took. And they're going to be highly correlated. To reduce the correlation, you're going to create a replay buffer. And at each point in time, while playing this game, you have a state, you took an action, you collected some reward, and then you went to the next state. And this is your agent's experience. Okay, so your agent experienced this behavior. The agent was in state S, it took action A, it collected some rewards, and then the environment gave it a new state for it to work with. These are going to be your data. So you're collecting your data on the fly. So you're going to create a replay buffer. You put that data inside this data set, and then each time that you want to optimize this, you just sample from this distribution, from this replay buffer to train this. And this way you hope that these are more IID data. And why is that? Because when the agent was experiencing this experience, they had different parameters. So the Q was different because it was different parameters. Okay, and maybe that's going to help this data set to be more diverse and IID. The question is how we're going to design your neural network. There is one way that the state is continuous. So the state, we are fine. These are just images. The state is the image or a couple of images concatenated channel-wise. So that is easy. The action is a discrete variable. We have two choices. We can either do one-hot encoding for these actions and then put that as one-hot encoded input to your neural network. Or alternatively, this is going to become more clear when I go to the next slide. But alternatively, if we don't do that, what do we have? An image goes in, a one-hot vector is going to go in, and a single number is going to come out. So alternatively, you can take an image and then output a vector rather than a scalar. And each dimension of that vector is going to correspond to a particular action. Maybe you went left, you went right. So now you have multiple input and multiple outputs. Basically, you are turning your inputs into outputs of the neural network. And it is okay because these are discrete and it's feasible. And that's going to give you your Q network. That was the input to the neural network is going to be the state, a bunch of images. The output is going to be vector valued. And these are going to be each entry of that vector is going to correspond to a particular action. In terms of the algorithm, this is going to give you your entire algorithm. It's going to be called deep QLearning. So if you hear that, that is this algorithm with experience replay, that is experience replay. How does the algorithm proceed? You initialize your replay memory randomly. So initially you have a random policy. You're exploring your space randomly. You're basically shooting in the dark. And then you're going to collect a replay memory. And it's going to have a capacity of n. You collected some initial data. They're going to be garbage, but you collected some data. And then you're going to initialize your Q network because Q is the only network that you have. And as soon as you know your network, your problem is solved. And the whole trouble is training that neural network, training Q. And you're going to initialize it again, randomly. So again, you are shooting in the dark initially. But then you're going to play your game m times, like a human would do. So a human would sit behind the computer screen and then play this game multiple times, m rounds. Sometimes the human is going to fail, sometimes the human is going to succeed, but then it's going to keep playing until the human gets a handle of the game and it starts winning. So we're going to do the same thing. You're going to have episodes. You're going to have m episodes. Initially, the only information that you have is the first screen of the game. So the first screen of the game is going to show up on your computer, and that's going to be an image. And then we're going to process it. So don't worry about phi yet. I'm going to tell you what that is. For the first sequence, it's very easy. You take the first image. And then your game is going to have T rounds, or you're going to stop playing after T rounds. You don't want to play forever. You get bored after T times of playing or T rounds of one episode. That's the maximum, but in between you might fail, basically. The ball is gonna, rather than hitting your object, it's gonna go down out of the screen and it's game over. So you could end before capital T happens. Okay, for reinforcement learning, we need to collect data on the fly. And we want our data to be as diverse as possible. We don't want always to do the same thing or have the same policy. We want to introduce randomness. We want to explore. So you want to balance the trade-off between exploration and exploitation. If you always do the same thing, you're going to collect rewards, but maybe you're stuck in a local minimum and maybe you can go to a better place, okay? So with probability epsilon, you're gonna select a random action. This is just random. Otherwise, you're gonna take a look at your policy, your Q network, and then you're gonna take the greedy strategy. So some percent of the time you're doing random stuff. Some percent of the time you're being on target. You're choosing your actions based on the Q network. And initially your Q network is also random. So everything is random initially. You're just exploring your space, your environment. So we are gonna execute action A in the emulator. So you're gonna go to your environment and execute your action. The environment is gonna give you some reward, and then it's gonna take you to the next screen. Okay, perfect. We are gonna collect whatever information that we just got. We were in a state S, we took action A, and then we saw the next screen. That's the next state. And this is where I'm gonna introduce the phi function, because you need to know a little bit of the history. Otherwise, you're not gonna know whether this ball is coming from the right or the left, whether it's going up or down, what is happening. We are gonna take as input the last 4 frames of our history. And you're just gonna stack them on top of each other. So you're increasing the number of channels of your image. Okay, that's the function of phi. And then now you have your data. You collected your data, the ones that you needed. You have phi t. This is your experience. Rather than it being st, it's now phi t. You took an action, you collected some reward, and then you're gonna create your next state because you just saw the next screen. You put that in your data set. And then you're gonna go ahead and sample from that data set a mini batch of examples, maybe 10 examples of previous experiences. Then you're gonna create your target. Now what you want to do is go back to your loss function here, write down your loss function, take its derivative with respect to the parameters, and do your optimization. First, you need to know what is yi. If the game terminated for any random reason, maybe you won the game, maybe you lost the game, maybe it was game over, maybe you hit the maximum number of iterations that you're allowed. In the last iteration, you just collect your reward. If this is the terminal state of the system, just collect the reward. Otherwise, collect the reward, and there is still gonna be some future going on. So make an estimate for your future if you follow the optimal policy. That's gonna give you RJ. As soon as you know your output data, you know your input data because you just sampled it. It's phi j, aj. So phi j, aj are the input. RJ and phi j plus 1 are gonna give you your output. It's gonna give you yj. You write down your regression loss, and then you can do gradient descent. That's your algorithm. So you're generating your data on the fly as you go. Any questions?
When we do the stacking for the S and the A, I'm guessing we just stack those as well. Like this phi function stacks the images as well as the actions as well as the, well, I guess ST.
So no, the way the algorithm is going to work is, I know this line is a little bit confusing, but the way that is actually getting implemented is you take the last 4 frames of your history. So you ignore your action and the state.
Okay.
So this is just a surrogate for your state. Phi t is a surrogate for st.
That makes sense.
Okay. Any other questions?
I was curious if this, I'm guessing this epsilon is something which they play around with a lot, and it's kind of like the like simulated annealing or the step size decay that we do in gradient descent. It's going to change over time.
Yes. So there is a lot of hype around deep reinforcement learning for good reasons, but then it is much harder to train them, to train this neural network in practice than it is to train a supervised model. It is much harder because you have a lot of fine-tuning to do. You have a lot of hyperparameters, and you're right. One of them is this epsilon. So I don't want you to get stuck in the hype around deep reinforcement learning. It has a fancy name, but in practice, it's very hard to get it to work. Okay. Any other questions?